So we have discussed earlier Faraday's law, and basically that was relating to how induced EMF is induced relating to the law through a change in flux. And what we'll be looking at right now is essentially the factors that affect the size of this EMF. So the law says that the induced EMF is related to, we can ignore the negative sign for now because that's just the direction, and out we care about the magnitude, but it's related to this term, which in words is the rate of change of flux. So quite simply, the bottom line is quite simple. The higher the rate of change of flux, then the larger the EMF. Well, that's quite simple. So why do we say factors then? Well, because I guess, well, it's very simple just to say that the higher the rate of change of flux, then the higher the EMF, and that is 100% true. There are many different ways we could achieve that. And it really depends on the scenario as well. So for example, if you're looking at a magnet moving into a coil, then you could achieve the rate of change of flux by, for example, the moving the magnet faster, or movement or the velocity of the magnet. So in other words, the velocity of the magnet will affect the rate of change of flux. Now, not only that, but if I had only one weak magnet versus one strong magnet, then you can also imagine that the stronger magnet would actually have a bigger change in the flux because, well, the B is higher. So anything that changes the magnetic field strength, such as the change of B, would affect change of flux. So in my example, the strength of the magnetic field, or the strength of the magnet here. There are many other ways to change B. I could, for example, also change B, not necessarily by the strength of the magnet. Well, we'll leave it to this example for now. If we look at this example, we could also consider how far away the magnet is. Because if you're moving the magnet like 20 centimeters away versus if it's 1 centimeter away, then the rate of change of flux will also change. So the distance of the magnet to the coil another key difference that we haven't really spoken about, and that kind of explains the N here, depending on how you view phi, is that really the phi represents, if you like, the flux throughout the coil. Now, I'm thinking of the coil as one whole thing. If you think of the coil as one single coil, then the more turns of the coil you have, the more rate of change of flux there is, which is why you might sometimes see this formula with an N representing the number of coils. So what we're saying then is that the number of turns of the coil can also affect the EMF because it will affect the rate of change of flux. So you've got how quickly the magnet's moving, how far away the magnet is. You've also got the distance of the magnet from the coil. There are all sorts of different things you can take into account when you're trying to determine the EMF using Faraday's law. But at the end of the day, the EMF equals basically delta phi over delta t. And then it's really anything that you can do to affect that. So we can take another look at other examples, but you might remember that phi equals BA. So really, in simple terms, if it has an effect on B, then it can have an effect on phi. If it has an effect on A, it can have an effect on phi. And if you have an effect on T, then it can have an effect on the rate, which therefore means it will have an effect on the EMF. So thinking about it this way, the effect on T would be like the velocity that we were talking about. It changed the time involved. In effect on B, well, that was, for example, the magnet strength in our earlier one. You can think of the number of turns maybe as an area, like you just got more area. But I can change it in more ways, right? Because remember, it's not only about a magnet moving through a coil. I could, for example, have a coil in a magnetic field. Or I could have a coil moving through a magnetic field. All of those are possible. But let's just keep it with a coil in a magnetic field. Then in my example, now, how could I get a rate of change of flux? Well, I could move the coil and I could move it faster or slower. So that's possible too. So that's the velocity of the coil. That's nice and easy. But I guess I could also change the area of the coil, right? Because no one ever said the coil can't be changed. Maybe I could squish it into a very, very, very tiny thing. And then there's not much area. So if that's allowed, and there's not necessarily any reason it can't be, the shape or area of the coil could be influenced. You can change that. And then I haven't really given you any context as to how I got this magnetic field, whether it's from a permanent magnet or if it's from an electromagnet, but I could simply just directly vary B. You can make B stronger or weaker. And if it's from an electromagnet, maybe I could do that by increasing or decreasing the current that creates the magnetic field. So you can see that there are many different ways that you could influence the magnetic field or the area or the time, all of which will affect the rate of change of flux, and therefore all of which can influence the induced EMF.